Verify that the function f of x is equal to x to the 2/3 power satisfies the two hypotheses of the mean value theorem on the closed interval from 0 to 1. And if it does, find all the numbers C that satisfy the conclusion of the mean value theorem. So remember, the two hypotheses of the mean value theorem are that the function needs to be continuous on a closed interval from a to b and differentiable on the open interval from a to b. So our first order of business is to determine if this function is continuous and differentiable. And I know we could certainly pull out our calculators or Desmos and take a look at the graph, but I'd rather think about this a little bit before we take a look at what the graph looks like. And one way to do that would be to rewrite the function. We know that f of x is equal to x to the 2/3 power could be rewritten as the third root or the cubed root of x squared. And this may give us a little bit more insight because we should know something about a basic cube root function. So just a side note, if we go back to just our knowledge of basic functions, let's just look at the basic y equals the cube root of x function. So I'm not looking at the cube root of x squared, but just the cube root of x to help you tap into some prior knowledge that may help you then in this analysis. We should know that the cube root of x function has a shape something like this. And we have previously discussed that at the origin at 0, 0, if you think about the tangent line on the cube root of x at 0, 0, the tangent line would be vertical. And a vertical line has an undefined slope. So there's no derivative at 0, 0. So we know that is true for all cubed root functions. There is a little bit of weirdness. So we would assume then for this function, the cube root of x squared, there's likely going to be a little bit of weirdness with the derivative when we take a look at 0, 0. Now, let's erase the cube root function and let's actually compute the derivative of this function right now. So the derivative of the cube root of x squared, now we know it would be more beneficial to think of the derivative from the original x to the 2/3 power, so we can just use our power rule, will be 2/3 x, and then remember we're going to subtract 1 from our exponent, so that will leave us with x to the negative 1/3 power. And if you do a little rewrite on that, we know that that's going to end up being 2 divided by 3 times the cube root of x. So you can see we definitely have a domain restriction in this derivative. We cannot have 0 because we can't divide by 0. So there's definitely a problem in the derivative at 0, which indicates that the original function is not differentiable at 0. So differentiability, we know it's not differentiable at 0. It would be differentiable everywhere else because the domain of this derivative here is all real numbers except for 0. So when you look at your interval, the interval given was from 0 to 1. It is not differentiable at 0, but remember, on the mean value theorem, the second condition says it has to be differentiable on the open interval. So that's okay that it's not differentiable at 0 because we're not including 0. It's differentiable on the open interval from 0 to 1. So we went a little out of order with that discussion. Let's go back and talk about continuity. We know that all root functions are continuous over their domains. So in this case, we have a cubed root function. That's definitely going to be continuous over its domain. And then inside of this cubed root function, we have an x squared function. And the x squared function is a polynomial. And that polynomial, all polynomials are continuous over all real numbers. So we have a polynomial inside of a cube root function. That makes this a composite function. And so this is the composite of a root function and a polynomial. Therefore, we do know that this is going to be continuous over its domain. And the domain of this function is going to be all real numbers because remember, we can have positives, we can have negatives, we can have 0 inside of a cube root. There's no restrictions. So our domain's all reals. Now, since this question asked you to verify that the function satisfied the mean value theorem, it's important that you actually write a sentence explaining your thinking regarding why this theorem does apply. So that's what I have here. F of x is the composition of a root function and a polynomial. So it is continuous on all real numbers. We determined that because of the domain of the original. And it is differentiable from negative infinity to 0, union 0 to infinity. And remember, we determined that because we found the derivative and we saw that 0 was not in the domain of the derivative. So therefore, the function was not differentiable at 0. Therefore, the mean value theorem does apply. Now, at this point, if you wanted to grab Desmos or your calculator, it would be a great idea to actually take a look at the graph because we've done all this analysis. And you will find out that this graph has this unique shape, sort of looks something like that. That's the graph of the original function. So you can see that the domain is indeed all real numbers. However, we definitely have a cusp at 0, 0 here, which explains why the function is not differentiable at 0. So all of that work was for the verification. And now we want to go ahead and do the work to actually find the C value. So remember, the mean value theorem states that there will be a value where the value of the derivative is equal to the average rate of change from A to B, which is f of B minus f of A, all divided by B minus A. So we've already done half of this. We have the derivative already. What we need to do now is we need to determine the average rate of change. And graphically, just a reminder, that's basically the slope of the secant line, also considered the average rate of change. In this case, we're looking for that average rate of change from 0 to 1. So we will just compute f of 1 minus f of 0, all divided by 1 minus 0. F of 1 is going to be just 1. F of 0 is 0. So we get that the average rate of change from 0 to 1 is just 1. Now the derivative, remember, is the slope of the tangent line, or the instantaneous rate of change at a particular point. And we have already determined our derivative, f prime of x. You can leave it as f prime of x if you want to. You could also write f prime of c. That's really up to you. But I'll take that from above. Our derivative we found to be 2/3 x to the negative 1/3 power. And so now the mean value theorem says there's going to be a value of x somewhere from 0 to 1 where these two are equal. So we're simply going to set these equal to one another. In other words, the derivative, the instantaneous rate of change, or slope of the tangent line, must equal 1, the average rate of change, somewhere on the interval from 0 to 1. So we need to solve this equation. Here comes our algebra. So for me personally, that negative exponent, I don't care for that. So I would prefer to rewrite our derivative like we did earlier. I'm going to write that as 2 divided by 3 times the cube root of x is equal to 1. That seems easier to algebraically solve. We can multiply both sides by 3 times the cube root of x. Please know this is not the only algebraic way of solving this equation. There are a variety of methods. So if you solved it a different way, good on you. Then I'm going to divide both sides by 3. So 2/3 is equal to the cube root of x. And then I will raise both sides to the 3rd power, or I'll cube both sides. And that's going to leave me with an x value of 8/27. So again, this is our value of c. You could call it c if you wanted to. It's an x value. It is in between 0 and 1, and it is where the average rate of change is equal to the instantaneous rate of change. So just to visualize that one more time, if we think about the original function here, which was x to the 2/3 power, and we were really just looking at the interval from 0 to 1, let's just say we call this 1. So if we were to go ahead and look at the average rate of change, or the slope of this secant line here, so in blue, the slope of the secant line, we found that the slope of that line was 1. And The mean value theorem says somewhere between 0 and 1, there's going to be a point where the slope of the tangent line is the same. So I'm just eyeballing this so you can visualize what the theorem is saying. But imagine this would be a tangent line, and it's going to be tangent to the curve at just one point. The slope of that tangent line is also going to be 1. So these lines are going to be parallel. And if we take a look at this point of tangency, and we look at that x value that we just found, we found that that x value, what we're calling our c value, is 8/27, 8/27. The point where the instantaneous rate of change is equal to the average rate of change.